Yeah. So let's start. So, very basic question for today. Can you guys tell me what was this week about? What did they discuss in this week of forests and their management? Has anybody gone and checked out the lectures or just looked at, you know, what was this week about? Okay. So, this week's in Forest and the Management, they basically discussed mensuration, forest mensuration. How do you measure different attributes of trees inside forests? And the major lectures talked about measuring tree diameter, tree height, and the basal area, the stand basal area, and spacing between trees in stands. So, that was what this week was all about. And coming to the first very basic question, what is the shape of a tree? So, what comes to your head when you think about the shape of a tree? Like, what does a tree look to you? Is it conical? Is it cylindrical? Is it some other shape? Is it paraboloid? What do you think? What does a tree look to you like? Would anybody like to say something about what they think when they look at a tree? What according to them is the shape of a tree? Okay, so when we look at the diameter of a tree and we compare it to its height, there are three different zones. There are three different zones, as you can see in this diagram. The topmost being conical, then it's paraboloid, and then it's neeloid at the bottom. Or and sometimes it's cylindrical. So there are these three different zones when you look at how the diameter of a tree changes with its height. So y-axis is height here, x-axis is diameter. So you see that the tree starts out broad, then it starts becoming a little narrow, and then it's narrower when you reach the treetop, right? That's how the stem of the tree changes with height. And to measure the diameter, if you give it by x in relation to the height, for the three different zones, you follow these three different formulae. So basically, how the diameter of a cone is related to the height of the cone. So for the conical zone, you measure it as y is equal to kx. Here we are putting square so as to just keep it uniform across the equations. Then for a paraboloid, y square is equal to kx, where the diameter is related to the height to the first power and not to the second power of height. And there's neeloid, which is the one at the bottom here, and this follows the equation y square is equal to kx cube. Okay, and an important thing is the tree stem is called the bole. So this is a new terminology here, that the tree stem is called a bole. It will be used later across the lectures. So yeah, so if you look at the shape at the form of a tree, basically what we're talking about is mostly the bole or the stem of the tree and how it changes with the height of the tree. And different trees have different shapes. You have some trees which are very straight and only at the top have a canopy. So those would follow a cylindrical shape. Then you have trees which are very broad at the bottom, might have buttress roots, and then they go on and become narrower at the top. So there are these different shapes of trees which we find. And when I was asking you whether they're conical, cylindrical, or paraboloid, you could have said any of these because trees have a lot of different shapes. Now, this is what the neeloid portion, this is what a tree looks like, and this is what a neeloid looks like. And when you compare the diameter with the height, and so a frustum of a neeloid is basically when you cut down the top portion of the neeloid, which is conical, and this portion is called the frustum of a neeloid. And when you compare the height with the diameter here, when you follow that formula, y square is equal to kx cube. So here y square, if y would be the diameter and x would be h here. So kh cube. K is a constant used. And if you look at the middle portion of a tree, that's like a paraboloid. And if you compare the formula here, then y is equal to y square is equal to kh. Okay. And for the topmost portion of the tree, that is similar to a cone. So when you compare it, then here you see that y square is equal to kx square, or y is equal to kx. So that's what the three formulae for the three different portions of the tree, as you can also see in this slide. So this is conical shape, paraboloid, neeloid. And these are the three formulae. Okay, moving on. So here you can see again, if you see, if it's cylindrical, then the radius related to the is not related to the height of the, because x to the power 0 will basically be 1, so the radius is independent of the height of the cylinder. For cone, it's related to the first power. Basically, if you under root x square, it will be x, so y is equal to kx. Here y is equal to k root of x. So, because y square is equal to kx, as we saw in the first slide, and here y square is equal to kx cube. So, this is how different formulae are followed for these different shapes for relating the radius or the diameter with the height. And if you think, uh, yeah, anybody has any doubt? Okay, and if you think why we are talking about y, which is showing radius here and not really the diameter, basically diameter will be 2y, and if you take 2 to the other side, it will just join the constant. So that's why whether you're looking at the relationship of radius or diameter, it will still be the base of the relationship will be the same, because 2 is again a constant. And what is the form of the tree? So when you talk about form, it refers, or of in general form of a structure, it's basically it refers to the shape of a solid. Like what is the shape of that particular solid? And in the tree, we're talking about the ratio of the diameter to its height, and it is determined by the power of x, as we saw. So basically, the relationship that we saw is y square is equal to kx to the power n. And in the case of the tree, this n could be 1, 2, or 3. It is 1 if it is a paraboloid, 2 if it's a cone, and 3 if it's a neeloid, right? So that was about form. Then coming to the taper of a tree. Can anybody guess what taper of a tree would be referring to? Like what are we talking about when we talk about taper? Can anybody would like to take a guess of what we might be hinting at when we're talking about taper of a tree? Anyone?
Maybe the gradual decrease in the tree stem diameter, that the thick base to finer tip.
Yes. Very nice, Tarsya. That's correct. Basically, when we talk about the decrease in the diameter as we go higher in the height of the tree, so the narrowing of the diameter of a tree in relation to increase in the height of a given shape or form, it's called taper. Here we're talking about the tree, but in general, it could be of any shape or form, and that's basically what is taper. And the characteristics of this are that it is measured in terms of centimeters per meters of the stem length. So how much centimeters of the diameter are decreasing with meter increase in the stem length. So if you're measuring height in meters and diameter in centimeter, it could be that. Otherwise, it's a dimensionless quantity, because both of these are basically, so it's just a rate of decrease in the diameter. Both of these are just measures of length. This could also be in meters, and then it's a dimensionless quantity. It's just the rate of decrease of diameter as we go higher in the height. So that's tapering. The equation used to measure the taper of a tree is, as we said, if you look here, if you measure here, we have a diameter of di. At the base, we have a diameter of d. And if you look at delta d, what is the change in diameter? It will be d minus di. Why d minus di? Is because d is bigger than di. As we go above, we're saying that it decreases. So d minus di, and taper will be delta d divided by height minus 4.5 feet here, because here we are taking the d or at this height. So you have to subtract this from hi, right? Because this much is hi. So that is taper. Delta d by the height by which those two diameters are separated. Okay. I hope this is clear. Moving to the taper and form. So different forms have different taper. Here, if you see this cone, in this conical form, you'll see that the diameter would decrease much more rapidly than this paraboloid, even if both those have the same height. So for the same height, this would have a higher taper than this because it's very steeply decreasing the diameter for the cone. Here we have these three different these six different forms. With TR1, there's no decrease in diameter. Then with 0.83, some decrease in diameter. Then it decreases more and more and more. And as it becomes more conical, there's a sharp decrease. Okay. So as the value of the taper decreases, the difference sharply decreases, at least in these images. Moving on to theories of tree form, we're talking about why are trees in the shape in which they are. So, can anybody tell me what are the different theories of tree form? Why do the trees take the form that they do? Anyone? What are the different theories for how the trees are shaped, or what is the form of a tree? If nobody would like to take a guess, we have one theory which is based on the nutrition and water conducting theory. It basically talks about how the tree form is shaped by the distribution of nutrients. How, as nutrients and water get distributed across the tree, that basically affects the tree form. So as photosynthetes are produced in the crown, basically photosynthetes are the substances produced during photosynthesis. So as the molecules or nutrients are produced in the crown after photosynthesis, they are distributed downwards through the tree stem, and they influence the cambial activity, which results in the stem diameter. So they will affect the activity in the cambium, which is basically one of the layers in the tree stem, and that will result in the tree in the stem diameter. And when it comes to water conducting, that theory suggests that the stem should be shaped in such a way so that the water transport can be maximized from the roots to the crown efficiently, so that the water can be transported efficiently from the root to the crown. So if you wanna increase the efficiency with which you transport water, basically taper will help you with the rising of water above the tubes, above the xylem across the tree. So that is how the nutrition and the water conducting theory basically explain tree form. According to nutritional theory, as nutrients are produced and conducted downwards, they basically affect the activity in the cambium region, and that's how the stem diameter increases. And according to the water conducting theory, in order to uh, optimize the water conduction in the tree, the taper in the tree happens so as to maintain hydraulic conductivity. Okay, that's the first theory. Second theory is basically the hormonal theory, which actually talks about how the growth hormones in a tree are produced at the apex. So, according to this theory, the tree form, it depends on the distribution of growth hormones, how they're distributed throughout the tree. So, it proposes that these growth inducing hormones, they're actually produced at the top of the tree, at the canopy, at the apex, and um, they are the ones that actually stimulate cambial growth, and they control the shape. So as they get distributed down across the tree stem, they again, these also affect cambial growth, and they lead to the different shapes in the tree. So in the apex where the hormones are high, sorry, from the apex where the hormones are high, they get distributed downwards, and downwards as they reach, they start increasing the activity of the tissue in the cambial region, and that leads to the growth of the stem or increasing the girth of the tree. Okay, so both nutrients and hormones, when they reach downwards, that's how they will lead to an increase in the girth of the tree. So this is similar to the nutrient theory, if you notice. So that's what the hormonal theory says. And the last one, which is the most famous one, which is the Metzger's theory or Metzger's theory, which talks about the mechanistic part behind the tree form. It basically says that you can consider the stem of a tree like a cantilever beam. And what is a cantilever beam? It's basically a beam of some material which is anchored at one particular point. So here you can see in this image, the tree is anchored at the ground. So at the base of the tree, it is anchored. And above that, there is no place where the tree is anchored anywhere. That's one point where it's anchored. So that's why it is similar to a cantilever beam. And basically, there's wind that acts as a force against this beam because wind is blowing or wind is flowing, and it exerts force onto the tree. And the tree stem tapers in order to ensure maximum stability, because the maximum amount of wind pressure will be at the anchor point. So in order to prevent the tree breaking, it will add more and more material to the base of the tree, so that the base is thick and strong and it can take the pressure of the wind. And as you go up, it's going to reduce its diameter or the girth, so that the wind pressure reduces, and that gives it stability. So it results in a cubic parabolic shape to resist bending stress at the base, because the maximum amount of stress, as I said, will be at the base because of the wind force. So if you look at this image here, you see that this is the maximum amount of force will be applied here, and as you go above, the force decreases. So again, coming to the features of the Metzger's theory, so this is what a cantilever beam looks like. This is the support anchor at one point, which we see is at the base of the tree, and this is where the load is getting applied. So the wind applies a lot of force here, and at the base is where the cantilever needs to be strongest so as to prevent breaking of the tree. So the tree stem, according to this theory, is equivalent to a beam of uniform resistance. Now, this is important to keep in mind that the tree, according to this theory, has a uniform composition. For example, like the cantilever beam. The cantilever beam has a uniform composition throughout, it's made of the same material. So, according to this theory, the stem, has the same material throughout, and it has a uniform resistance to bending. So, at any point, it can resist the bending force equally only. Uniformly it can resist the bending force. In that way it behaves like a cantilever beam. And then when wind applies the bending force to this beam, maximum stress is applied at the base. So the base is the one that experiences maximum stress. Therefore it needs to be reinforced with addition of more materials. Since the entire tree is assumed to have the same composition, so you have to put more material at the base so that the base is reinforced and strong, and the stress reduces as we move upwards, and therefore less reinforcements are required. Okay, I hope this theory is clear for everybody. Basically, we're just equating the tree to a cantilever beam, and we are saying when we apply force to it, maximum stress comes to the base. And because the composition of the entire beam is uniform, what the tree can do is add more material to the base, make the base broader so that it can handle this stress. Okay, so therefore, the tree has a tapered form. And Metzger's actually proved this for a lot of coniferous trees, for a lot of conical shaped trees, but did not really prove it for other forms of the trees as much. So that's like one of the caveats of this theory. Okay, when we come to the maths behind it, if you look here, if you compare this tree to this cantilever beam, at this edge, P is the force which is applied at the free end. So P is the force that the wind is applying at the free end. L is the distance of a given cross section from the application of force. So if you're talking about L, it's the length of the given cross section. So here we can actually talk about, in the case of the tree, we can talk about the full length of the tree, because we want to talk about the basal diameter where the force is maximum, right? So here they're actually talking about the diameter of the beam at this particular point, but for the tree, we can assume that we're talking about the diameter at a lower point at the base of the tree. And then L would be the height of the tree, right? So then by the simple rule of mechanics, or the bending stress, which is kg per centimeter square, is given by this formula, which is S is equal to 32 PL divided by pi d cube. Coming to how this formula gets derived, basically the bending stress, which we said S is 32 into PL by pi d cube. Basically, this 32 PL comes from some mathematics, and P, as we said, is the force, that is applied by the wind. L is the length or the height of the tree that you're talking about, and D is the diameter from the point of force application to where you measure the diameter. So this is the formula for the bending stress. P here is W into A. W is wind pressure per unit area, and A gives you the crown area. So, what is the area of the crown and how much wind pressure is being applied per unit area? Then S would become 32 into WAL divided by pi into D cube. Now, as you can see in this equation, 32 into W into A into L by pi, all of these are constants. So, S can be equal to K, sorry, W, A, and pi, these are constants, not L. So S can be given by K into L by D cube. And because now we are saying that the material is also homogeneous, S is also a constant. So the bending stress throughout the bar or the stem of the tree is actually constant because it's a property of the material of the tree. So it's the property of the material of the cantilever beam. And now, because we're talking about the tree, it's the property of the tree stem. So the bending stress is constant throughout. So 32 into W into A into L by pi d cube is a constant. So it leaves you that basically d cube is equal to 32 into W into A into L divided by pi s, where everything is a constant except for L. So d cube is basically related to L. So, as we talked about in the first slide, where we are comparing the diameter with the height, basically, this is talking the same. It's comparing the diameter with the length or the height of the tree. So, this is what is going on here also. So, but according to Metzger's formula, basically, it's d cube, which is related to the height, right? Earlier, we were talking about the conical shape, the paraboloid shape, and the neeloid shape. But according to Metzger's derivation, it's d cube is equal to k into L. Where do we use this theory? Basically, if you talk about wind action, so when you talk about trees inside a dense forest, because they will face less wind action, less wind pressure, they will become longer and they will have a cylindrical bowl. So because they will have lesser and lesser wind action, they'll not taper so much and they'll become straight and cylindrical. Because according to this theory, they taper because there's high wind pressure and they need to add more material to the base. So if there's not much wind pressure, they don't need to taper. They can become cylindrical and straight. Trees that, on the other hand, grow in isolation in windy locations, they face a lot of wind pressure, which leads to a shorter tree and a more tapered bole. Now, if you compare these two trees, you will basically yourself be able to figure out that timber which comes from trees growing in dense forests is much better and more profitable over timber which is growing from trees which are growing in isolation. Because when you talk about timber extraction, you need a lot of tree stem or the bowl, and you want it to be cylindrical, more or less equal in shape. If you have a tree which is wider in one place and then very narrow in the other, that's not very useful for timber extraction. So when you're talking about timber extraction, you would want to go for trees in the dense forests. So that's basically where silviculture will come into play. If somebody is growing their stand for extracting timber, they should grow them in a high density so that not a lot of wind uh, affects the trees. Caveats of this theory is that it does not explain all the three tree forms. It only talks about the conical form of the tree. And the assumption that the tree has a uniform composition is not really realistic. We don't know whether trees actually, I mean, we know that trees don't really have a uniform tree composition. They can change what kind of materials they deploy in which section of the tree, right? So they don't necessarily need to put like equal composition of their nutrients or the of the equal composition or similar composition throughout the stem, throughout the length of the stem. They can actually put heavier materials down and lighter ones up so that so as to maintain the stress and all of that. So these are some caveats of this theory. Now, coming to the factors that affect stem profit of individual trees, or like how much profit you can do from individual trees, or how better a tree will give you timber and things. Basically, you have different factors. One of them, as we saw, it's the social position within the stand. So can anybody tell me which social position would be better to get to extract timber from a tree, like which tree, or like whether a tree at the center of the stand will be better for timber extraction, or will the tree at the edges be better for timber extraction. So which social position would be better to get more profit from timber extraction for a tree? Can anybody think about it, like from the slides that we just discussed? What do you think, which social position is better for getting high returns and for getting good quality timber? You can either type it out in the chat box, or you can unmute yourself and take a guess. Nobody? So, because we're talking about wind action, and if there's more wind action, then the tree will be more tapered. If there's less wind action, the tree will be like more straight and cylindrical, and cylindrical trees are better for timber extraction. So, if you think about it, social positioning within a stand, if the tree is inside the stand, away from a lot of wind action, then the central positions will be better for getting better quality timber. But if a tree is at the periphery, at the edges, because it will face a lot of wind from, because it's not protected from any more trees, it's basically at the edge, then it'll get a lot of wind action, and those trees will be more tapered compared to the ones in the central positions. So if you talk about social position within the stand, central trees are better for timber extraction. Talking about site of cultivation, if you're in a windy area, if you're in a slopey area, then those will have more wind action. And if you're in a level ground, you'll get less winds, and basically that will be better for um, getting better quality timber. Or it also could be talking about, when you talk about site of cultivation, could also talk about the type of soils you have in different areas, and which ones are better for tree growth. Coming to silvicultural treatments, you talk about stand density. If you have a more dense stand, then the central trees would have less wind action. Basically, that will help you. Planting spacement, how much space do you give to the trees? If you are planting trees closely, or like not, if you're planting trees too far away, then they will experience more wind. If you're planting trees closely, then they will experience less wind, and that will be better for getting better timber. Fertilizer, how much fertilizers you apply, that will tell you, like that will improve the quality of wood that's coming out. And then there's genetic parameters, because of course some trees will be genetically better than others at giving you a strong having a strong stem, having a strong timber which can be extracted from those trees. So these are different parameters. What is the position within the stand? What is the site of cultivation? Where are you cultivating the trees? And then the different silvicultural treatments, how densely you plant your trees, how much space you give. Basically, stand density and planting spacements is one, it's the same thing. How densely you put the trees, or how much space you leave between the trees. And then fertilizer application and genetic parameters. Basically, some trees will be better genetically at giving you high quality timber compared to the other ones. Moving on to form factor. So, when you talk about form factor, it's basically a number which is used to describe the tree form. We already discussed what is tree form. Tree form is basically the shape of the tree. And so, form factor is also just a single number to describe the tree form. And it's represented by this dimensionless ratio of what is the volume of the tree divided by what will be the volume of a specified geometrical solid with a similar height and a similar basal diameter. So when you're talking about a geometrical solid, mostly they compare it to a cylinder. So how is the volume of a tree divided by volume of a cylinder with same height and same basal diameter? How are these two related? And that will give you an idea about what is the tree form. It's important to estimate the amount of timber present. So if the form factor basically is closer to 1, that means that the volume of the tree is similar to the volume of the cylinder of the same height and diameter. That would mean that, okay, it will give you high amounts of timber, and as the form factor goes down, the amount of timber will be less and less, because it will be more tapered, right? Moving on to types of form factor. there are different types of form factor based on where you're getting the diameter from. So there's one called the absolute form factor if the diameter is used as the basal diameter, like the diameter at the bottom of the tree. But usually it's very difficult to get the basal diameter or get the diameter from the base of the tree, because if the tree is in a very dense undergrowth area, you can't really manage to reach the tree and get the diameter. Other thing could be that the tree has a buttress root or something like that, and then again you can't get a basal diameter because if the tree has buttress roots, you won't really get a correct measure of what the diameter is, because they are very protruding and very uneven to get the diameter from. So what basically is done to make our lives easier is to get a false form factor, which is actually by using the diameter at breast height. And what is diameter at breast height is basically, usually it's considered to be 1.37 meters. So if you stand, if an average heighted person goes and stands and puts their hands out like this, then that is at breast height, and that is where they take the measurement of the diameter of the tree. So that's called diameter at breast height, and that's usually considered to be 1.37 meters, but it's different in different countries. And then there is true or normal form factor, which is a little bit more scientific, which talks about using diameter at 10% height of the tree as a reference. So if the tree is 50 meters, and then basically 10% height would be 5 meters. So 5 meters? Yeah. So that would be the reference point of taking the height of the tree. So basically, that is how you. There are different form factors. Absolute form factor, which uses the diameter at the base of the tree. False form factor uses the diameter at breast height, and true or normal form factor uses the diameter at 10% height of the tree as a reference to calculating the form factor. Fine. Moving on to form quotient. So form quotient is different from form factor. They're not the same things. Okay. So to keep that in mind, form quotient is not the same as form factor. It's now a single number which depicts the rate of decrease in stem diameter. It's a ratio of diameter at two different heights of the tree. Earlier, we looked at tapering, which is how the diameter is decreasing with height. In form quotient, you're basically talking about how the diameter is decreasing. So you're basically just comparing the two diameters at the different heights. So you're not subtracting the diameter, you're not doing delta D by H, you're just doing D1 by D2. So it's a ratio of diameters at two different heights on the tree. So form quotient, as I said, single number depicts the rate of decrease in the stem diameter. Where so now there are different types of form quotients which depend on where you are measuring D or dx. So as before, they also depend on where the diameter is being taken from. There's one is the false form quotient, where you compare the diameter at 50% height of the tree. So if the tree is 20 meters, you're taking a height at 10 meters. So at 50% height of the tree, and you take the ratio with the breast height, the diameter at breast height. So that is the false form quotient, where you compare diameters at 50% height of the tree with the diameter at breast height. Then there is a true form quotient, where you compare the diameter at 50% height of the tree to diameter at 10% height of the tree. And then, okay, so there are these two basically form quotients. There's no absolute form question. Or maybe, yeah. Moving on to the second lecture, which just talks about how to measure the tree diameter. So, first lecture mostly talked about tree form and tree shapes. If anybody has any doubts in those, you can ask me. The next lecture basically talked about how to measure the tree diameter, or how we're measuring the how to get the diameter of the tree basically at these different heights that we talked about. Right? To measure tree diameter, basically, as we talked, that the tree diameter tapers, and therefore we need to think of a standard point where we should measure the diameter, right? Because we're saying that the diameter, not every tree is cylindrical and straight, so you can't measure at any point and get the same diameter. So some trees taper, so you need to come up with a standard point where you would measure the diameter for trees so that they can be comparable to each other, right? So when you talk about it, standard is one of the standards is to measure at breast height, which is dbh. But as I said, it is different in different countries. USA has a height of 1.37 meters. Most other countries use 1.3 meters, but yeah, 1.37, 1.3 meters, it's fine. And but Japan and Korea use 1.2 meters, so it's not uniform throughout countries. So that's a little bit problematic when you want to compare trees across countries. Now, for measuring tree diameter, it's related to the you can either measure it in two ways. It can be measured over the bark, which is called DOB. So if in this image you think of this brown area as the bark and this is the inner region, then this white line is DOB, where you're measuring the diameter over the bark, and this one, the black line, is actually DUB, which is under the bark. So, how are DOB and DUB related? Basically, diameter over the bark is diameter under the bark plus 2 into the thickness of the bark. So, if this white line, this small white line, is the thickness of the bark, you'll have to add 2 times thickness of the bark into the uh, diameter under bark. I hope this is clear. It's very basic. So if you have the bark of the tree, so because it's gonna be added on both sides, because if it's the radius, then you'll add it on one side. If it's the diameter, you'll add twice of it to the diameter, right? So that's how diameter over the bark is related to diameter under the bark. TB is the thickness of the bark. There are some formal rules to measuring the diameter of a tree. Some of these are: if the tree is on level ground, then you measure at 1.3 meters vertically, basically the breast height. You measure it vertically. So here the second image shows that the tree is on level ground, so you basically take this 4.5 feet or 1.3 meters vertically. But if the tree is on slope, you measure it on the uphill side. So the tree is on a slope, you have to measure it on the uphill side and not on the downhill side. Can somebody tell me why is that so? Why should we measure the tree on the uphill side and not from the downhill side? It's like you can take a guess from looking at the image itself. What do you think will happen if you measure DBH from the downhill side for a tree which is growing on a slopey area? Anyone? It's a very basic question. You can look at the image and also take a quick guess. You don't have to be correct. Just what do you think what will happen if you measure a tree from downhill, not from
Or
uphill?
stability or the safety reasons.
Safety reasons, okay. Anybody else? Why do you think it's unsafe to measure it from downhill? Anybody else would like to think about why should we be measuring it from uphill and not from downhill? Okay, I mean a very simple explanation would be if you measure it from downhill, it's basically going to give you a wrong estimate of the diameter, because I mean, it's gonna give you like a thicker DBH because it's lower from here. If you measure 1.3 meters, it's gonna be lower than the 1.3 meters you measure from uphill, and because uphill is where it touches the ground sooner than here, we basically should measure it from this point, because after that it can get like even more thicker, and this is where it's basically start to root. Right at this point, it'll start to root itself. So you should measure DBH from this point to get a more accurate reading, because if you do it from here, you might end up getting like a thicker DBH than which will be incorrect than the other one. And yeah, I don't know how unsafe it might be from measuring it from downstairs. Downhill. I think that should not matter. Anyway, next point is in case of an irregular cross section. If the tree stem has an irregular cross section, then you basically should measure two diameters, one above and one below the DBH. The average of the two should be used to estimate the diameter. So if you have, for example, in these 6 and 7 one, in these, if you have like an irregular cross section, for example, here you have a protuberance here, so you should take one measure which is above the protuberance, one measure which is down the protuberance, and then you should average out the two to get the estimate of the diameter. Should not take the diameter over the protuberance, take one above and one below. Okay, so that's basically how you do it. If you're, I mean, that is if your DBH is in the protuberance. Okay, so if the tree has like a bulge at the breast height, then you take one measurement above and one below, and then you average them to get the correct estimate. Next, if the tree is not upright, then you measure it 90 degrees to the tree axis. For example, here the tree itself is leaning, it's not on slopy ground, it's leaning itself. So here you should take the DBH to be at 90 degrees to the tree axis. So if this is the tree axis, you should take it at the 90 degrees to the tree axis. Okay. Then, in case of buttress roots, for example, here you have buttress roots, so you should get the diameter above uh, the swelling. Even if the breast height, even if the buttress roots are still at the breast height, you should take the diameter even above that to get the correct measure. And if there is forking happening, if the fork, if the tree is forking into two, if the DBH is at if the sorry if the forking is happening below the breast height, then you should consider it as two separate trees. If the forking is happening above the breast height, then you should take one diameter, which is you should consider it as a single tree. So you can see here the forking is happening above the DBH, diameter at breast height. So here you take, consider this as a single tree and you take one diameter. If it's happening above, yeah, if the forking is happening below the DBH, then you measure two diameters and consider them as two separate trees. Okay. Then you talk about how to measure diameter in the field, how it's done there, out there. So one of the basic methods or is to use different measuring tools. One of them is calipers. You all might be aware of calipers. You would have seen them in physics lab or something. So basically, one is the fixed arm, one is the movable arm, which you can adjust, and this basically has the rod has the scale. So you put the fixed arm and then you adjust the movable arm so that the tree is basically inside both of them tightly, and then you measure what diameter comes out. So that's basically your diameter. So it's very straightforward. So for using, it basically directly measures the diameter. Points of the calipers touch the tree and they are always in sight. So because both the arms of the caliper, even the moving and the non-moving, are both in sight, so it's more useful because it tells you that you're actually getting a correct measure, and it's not like up and down or this. You can keep them at like 90 degrees to the tree axis, keep them perpendicular. So there's collect, because the second point is because arms of the caliper, they can actually press firmly and they can crush the loose bark, so that will give you a reduced error. The error will be less because the bark is crushed. Now, something that can also be done is that if you have unskilled people going out to measure the tree bark and you don't really trust what measurement they'll come back with, you can actually paint the caliper into different sections. Say you have the caliper painted as like 10 centimeter, 20 centimeter, 30 centimeter, whatever is the diameter. And based on that, they can just tell you that, okay, the tree is in the, say, till 10 centimeter, it's red, then it's green, then it's blue. They'll tell you that this tree falls into the red category, green category, like that. And then you can just get an idea of what are the different diameter classes in the forest stand. The results here are more robust than using a tape measure because of reasons we'll come to later. So, but the results that you get from vernier caliper or the caliper measurements are more robust than tape. And the positive and negative errors can cancel each other out. So, there can be some positive and negative errors with the calipers. So, if you have the caliper and there's moving arm, sometimes these arms they get bent in a way that this one says the fixed arm, this is the moving arm. Sometimes it can be bent like this, which will give you like an overestimation of the diameter, and sometimes it's bent like this, and that can give you an underestimation of the diameter. But sometimes this positive and negative errors can actually cancel themselves out, and that also makes it better than tape measure. But the second very easy way to measure the diameter is actually to use a tape measure. Now, can anybody tell me what the tape measure actually measures and how that's related to the diameter of the tree? What are we actually measuring by using a tape measure, and how will that be related to the diameter of the tree? Now, at least I'm giving you one hint here that the tape measure is not really measuring the diameter. So, what is it measuring, and how is it related to the diameter? Anyone? Take a quick guess of what the tape measure is measuring and how it's related to the diameter.
Maybe it's measure its circumference
Yeah, and how is that
and
related to the diameter?
it used to divided divides the length by pi and we get the diameter directly.
Exactly. Very nice. So basically, the tape measure will measure the circumference. So you get the circumference of the perimeter of the stem, and then you calculate the diameter as p divided by pi. So, as you said, which is correct, basically all of you should have been able to guess that. Basically, you get the circumference of the tree, and then you can use a simple formula to get the diameter. Here, yeah, we are assuming that the tree is more or less circular shape, which is one assumption that goes when we calculate diameter in this way using the tape measure. Because your tree could be elliptical, your tree could have a random shape. They don't always come in circular shapes, but yeah, that is the error that we are going in with. There are different types of tape measures. They can be a cloth tape, could be a reinforced cloth, could be a plastic, or could be a metal tape measure. Fine. So these are the different types of tape measures that are generally used in measuring trees. Some care you should use if you're using a tape measure. It should not be very old, because if the tape measure is too old, or if it's a cloth one which is too old, it might get stretched, and then it will give you like wrong readings for the circumference of the tree. The tape should be lying flat against the surface of the tree, so there should be no folds, no bends in the tape. When you're putting the tape across the tree, it should be carefully put so that it's entirely flat against the surface of the tree and there's no folds in it. Must be perpendicular to the axis of the tree. This is something to keep in mind. So when you're measuring the tree diameter using a tape measure, it should not be like come from up to down or down to up. It should be like flat 90 degrees to the tree axis. This is something that's difficult to take care of if you're measuring a huge tree. You'll need like multiple people so that they can, at least two people, to take a look that, okay, yeah, the tape measure is perpendicular. Because in case of vernier calipers or in case of calipers, you could actually look at both the arms and you would know that, okay, this is the correct measurement. But in the case of the tape, because you can only look at the tape on your side of the tree, you might not get an idea of whether it's going in the same plane or it's going slightly up or down. So you need to get an idea of that, and it should be perpendicular to the axis. There should be no knots or turns in the tape. And if the tree has a lot of climbers going around it, you should make sure that they are not included in the measurement. Either take your tape from an area within the climber or the tree, or you'll have to like cut out the climber before you get the measurement. And then you should store the tape carefully so as to avoid depreciation, so as to avoid like so as to save the tape for a longer time. Now, there are some advantages and some disadvantages to using tape measure to get the diameter of the tree. Let's see what these are. Basically, in advantages, as you might think, it's very convenient to carry. So when you think about those calipers, as you saw in the image, the caliper is huge. It has two big arms and it has a huge rod. It's sometimes very, very big based on what kind of trees you want to measure. So it's very difficult for, and they're made out of metals or they're made out of wood. It's very difficult for people to lug those around, carry those around to get the measure of the tree diameter. So they're very heavy to carry around compared to the tape, which is quite convenient to take around. Second thing, which is bad about the calipers, which I forgot to discuss earlier, is that those arms can become sticky and the loose arm might not move smoothly along the rod, and that might lead to some errors in measurement. But yeah, which is not a case with the tape. In the tape, a single measurement suffices even for irregular trees. Even if your tree is not circular and has like different wavy structures or is ellipsoid or something, one measurement will be fine. But if you're using a vernier caliper to say getting the tree diameter for an ellipse, you'll need to take multiple measurements, one at the major axis, one at the minor axis, and then only you'll reach at the diameter of the tree. So single measurement here suffices. While measuring the girth, the tape will be in contact with the entire surface, which is also a good thing, which does not really happen for the caliper. And it does not require constant adjustment. You don't really have to correct for zero errors all the time, which happens in the case of calipers. Some disadvantages of using the tape is that if the tree has a quite a rough bark, then positive errors can happen because it will give you an extra estimation of the diameter because of the bark. Then the tape may not be at right angle. As I said, it can go unnoticed even if it's not at the right angles, because you're standing at this point and you don't know what is happening on the other side of the tree. So you need to make sure that is not happening and it's at right angles all the time. And the elasticity of the tape can affect measurement. Like over time, if the tape loses elasticity, it'll give you a incorrect measurement. And as I said, the observer may not have a full view of the circumference if the tree is a big tree, and that can lead to some errors in measurement. Okay. So these are some advantages and disadvantages of using tape. And this was all about lecture 11, where we just talked about how to measure diameter. And the different ways of doing that is either using calipers or using a tape. And we discussed about the advantages and disadvantages of both these measurement methods. Coming to measuring height. So in the next lecture, we talked about how do you measure height. Basically, total height of the tree is the bole height plus the crown length. So they divide the tree into two parts. One is where branching starts, that's the crown of the tree, and below that, where there is like the entire bole without any branching happening, that's called the tree stem is called the bole, as I said in the first slide. So bole height plus the crown length is the total height. Bole height is the height below the lowest branch in the crown, and this is what has commercial value. So if you cut down the tree, this is from where timber will be extracted, and this has commercial value. Okay. There are two ways in which you can measure the height. You can either measure it directly or you can measure it indirectly. For direct measurement, you can put an instrument directly against the bark and measure. So if you have a tree in front of you, you can actually be carrying around a rod of known lengths. For example, say you have an extendable rod, which is like 10 meters, 20, 30, it can extend. So you can basically just measure directly by putting it against the tree and see till wherever you want to measure the height. That's one direct way of measuring the height. One is somebody can climb the tree, and from there they can throw a string down. And so you can attach a weight to a string, and somebody can climb the tree, and from wherever you want to get the height, just throw the string down, and then you measure the length of the string. That will give you the height of the tree. These are two very direct ways of measuring tree height, but most of the times they can be quite unfeasible to do in the field, so you end up using indirect measures. One indirect measure is by using similar triangles. So many of you might be aware of what are similar triangles. This is something we study in high schools, in the high school mathematics and trigonometry, where we look about congruency and we look at similar triangles. We'll refresh it here. But yeah, if for indirect measurements, you either use maths of similar triangles or you use trigonometry. Okay, so this is all about measuring height. And how do you use similar triangles? So this is a small refresher of what similar triangles are. Basically, their properties here, there are two triangles, XYZ and PQR. Both of them are similar. Why? Because all the corresponding angles are equal. So angle X is equal to angle R, angle Q is equal to angle Y, and angle Z is equal to angle P. So all these three angles are equal, and the corresponding sides will be in the similar ratio. So here, the side opposite to angle X, which is X, and the one opposite to angle R, which is R. So x by r will be equal to y by q will be equal to z by p. So that is what defines similar triangles. The angles are equal and the sides are proportionate. Okay, so they can be of different sizes, but the shape of the triangle is same. So how do you use similar triangle methods to get to the height of a tree? Is either you can use the shadow method or you can use Christen's hypsometer. So hypsometer is actually a term which is used for tools that are used to measure height, altitude, or elevation. So hypso is a term used for height, elevation, things like that. So hypsometer is a term used for any tool that is used to measure one of these. So in the shadow method, as you might already be thinking, actually, would somebody like to take a guess of what is the shadow method and how do you use that to measure trees? You might already be aware of this method of measuring tree heights. Anybody would like to take a quick guess on how do you use shadow method to get to a tree height? Think about uh, shadow method and think about similar triangles. Think about the term shadow and similar triangles, and how do you think you would come up with getting the height of the tree by using shadows? Anybody would like to take a quick guess? It's not that hard. Okay, if not,
Maybe with the shadow length of the tree and with the shadow of length of us known height like object like us, etc.
yeah, very, very good. So you're correct. So if you look at the tree versus you look at, say, you take a known length, for example, a pole, or you take us, you're correct. And then you basically, because of the sun's incident rays, if you're doing it at the same time for the tree and the pole, the angle of the sun's incident rays will be the same. Then you look at the length of the shadow. So here there are two triangles. One is capital ABD and one is small ABD. And as we looked already, this side would be proportionate to this side. So AD by small AD should be equal to AB by small AB should be equal to BD by small BD. So using this, you can actually reach to the length of the tree. So here, if you take tree height as x or capital AB, you see AB by small ab. Now, because we know the length of the pole, so we know small ab. And because we measure both the shadows, the shadow of the tree and the shadow of the pole, so you have capital BD and small bd. So from here, you can very simply get the height of the tree. So basic mathematics, I hope it's clear to everybody how you can use the shadow method to reach to the height measurement of a tree. If anybody has any doubts, you can ask me. So very easy, very like straightforwardly, you basically take the shadow of the tree and you take the shadow of uh, a pole or of a human being or something which is of known height, and then you measure the shadows in both scenarios, and then you know the height of the pole whichever you used. For that, you just use put it in the formula and get the height of the tree. Okay. Second one is Christian's hypsometer. Christian's hypsometer is basically this instrument which can either be made out of wood or can be made out of cardboard or something like that. And from here, you basically take it in your hand like this, vertically open it and take it in your hand. And then from here, you actually look at the if O is the eyes, what do you call it? The height of the eye. If O is the objective, as loose is used in the lenses case, you basically get these two triangles. So you put again you put a rod of some known length. So AB is a rod, say, of known length, and here you adjust the hypsometer to get the reading here, to get the reading of small AB. And AC is the height of the tree, and then you get this bigger reading AC, small a and small c. Now there are four triangles here that we want to consider in this case. One is OBA and O capital B capital A. These two are the similar triangles. So small O, small BA and O, and capital OBA. These are two similar triangles, and the other one is OCA and O capital C capital A. These are two other similar triangles. Now, as before, you basically use the proportionality of the sides. So here you see capital O small a divided by O A is equal to small ba and divide by capital BA. Okay, because these two triangles are similar. Then in the second case, O small a divided by O capital A again is now similar to small c small a and then divide by the height of the tree, which is AC. Now, because AC is unknown, you basically put these two are equal, OA by OA. So you put this BA divided by capital BA and CA divided by capital CA, and from here you get CA, which is the height of the tree. So again, here you use the mathematics of similar triangles, and you use this device called the Christian's hypsometer, from which you use it, you put it in front of your face, and you get like um, you have like an eyepiece from which you look. First you adjust it to the height of the rod and you get a reading, and then you adjust it to the height of the tree and you get the reading. So both these readings now give you a measured value, b small ba and capital small ca, sorry. They give you two lengths, and that you can use to measure the height of the tree. I hope this is clear. Anybody has any doubts in this slide? It can be slightly confusing, but it's yeah, it's straightforward if you understand it once, but yeah, it can be confusing in how this is happening. Okay, moving on to how do you measure the tree's height based on trigonometry. So you might be aware of this simple thing, or not so simple for some people. Basically, Pythagoras theorem. If you have a right angle triangle and you have these three sides A, B, C, then the two sides are A and B. A square plus B square is equal to C square, which is the hypotenuse, right? The height and the base and hypotenuse are related by the formula A square plus B square is C square. This is Pythagoras theorem. And here, between B and C, if you have the angle theta, then sine theta is basically A by C, cos theta is B by C, and tan theta is A by B. And this is the basic sine, cos, tan table for 0, 30, 45, 60, and 90 degrees. Now, I put this here for your reference. So when you guys are going through the slides later, you can look at this table. You guys might already be aware of this table. Basically, for sine theta from 0 to 90, it goes 0, half, 1 by root 2, root 3 by 2, and 1. For cos, it goes the other way around. And for tan theta, for 0 degrees, 0. For 30 degrees, 1 by root 3. 45 is 1. And then 60 is root 3. And this is undefined because it's basically the ratio of sine by cos. Anything, so 1 by 0 is undefined. Yeah. So how do we use trigonometry to get to the height of the tree? Here you can see there's a protractor to which a weight has been attached. So wherever you turn the protractor, that will give you what angle it is making with the. So this is basically what you point towards the tree, and what angle it's making, the weight will give you. So that's how in different ways you can measure the tree height. So one way is by using this Bloom Lice hypsometer. It's this tool which gives you the angle and the tan theta measurements of. So you're standing, so for example, you're this person standing here, and this is your distance A. Small a is your distance from the tree, and this much is your height, the eye level height. Above that is the height of the tree. Sorry, h minus your height, right? And you use the hypsometer and put it in so that your eye is facing the crown of the tree. So this is an eyepiece. This you put on your eye, and then you see towards the crown of the tree, and that will give you the angle. It's basically will give you theta, and using tan theta you can get h upon a. So it will give you this value from which you can get h, and h you add to your own height or your eye level height, and then you will get basically the height of the tree. So using this This meter actually gives you tan theta for some like given measurements. For example, if you are 10 meters away, 20 meters away, for these things, it will give you the tan theta directly and you can directly use it. But for others, you can actually just go and calculate it using a calculator. So it gives you the angle theta of the crown height from the person's eye view, eye level, right? This angle theta. And using tan theta, you can get the height of the tree. So that's Bloom-Lies hypsometer. So these are different ways in which you can measure the height of the tree. There are two direct ways basically. You just put a rod against the tree and get the height, or you make somebody climb the tree and throw a string down, get the height. Or you can use similar triangles by using shadow method, or you can use that Christian's hypsometer, or you can use trigonometry, and you for that you can use Bloom lights, or you can use a normal protractor to just get the angle of the tree. Okay, so that was that. Then comes the basal area. What is basal area? It's actually the area occupied by the cross section of the tree trunk. So near the base of the tree, what is the area occupied by the tree trunk? That is the basal area. It's given by this formula pi d square by 4. So basically it's pi r square, which is, and r is d by 2, so it's pi d square by 4, area of a circle. So we are assuming that the tree is circular in cross section, so by using that formula it becomes pi d square by 4. Okay, and the volume of the tree is actually the form factor multiplied by the volume of a cylinder. So like volume of the cylinder of the same diameter and height, so it's form factor into pi d square by 4 into h. Okay, form factor we discussed earlier. Can anybody tell me what was form factor? There were two things. There was form factor and form quotient. Can anybody tell me what was form factor? Anyone? We discussed
The shape of the tree.
shape of the tree is the form.
The shape
What
of
is,
the tree.
yeah, what is the form factor? So we discussed that form factor is a single number which is used to give you an idea about the shape of the tree. So literally from this equation you can get form factor. From the equation written in front of you, what is form factor? So basically, here you can see we're saying volume of the tree is form factor into volume of the cylinder. So we discussed earlier, form factor is a single number which represents the form of the tree or the shape of the tree. Form factor is volume of the tree divided by volume of a cylinder of the same height and basal diameter. That was what is form factor, right? So volume of the tree is given by form factor and multiplied by the volume of the cylinder. So this is basal area and this is the volume of the tree. So it's actually used, basal area is used in calculating the volume of the tree. Then there is stand basal area. Stand basal area is actually the sum of basal area of all the trees in an area. So if you're talking about a stand, so for example, say you have an area of 1 hectare, which is your land in which you have planted a lot of trees. So what is the basal area of all the trees in the stand? So that's the stand basal area, and it's expressed as per unit area of land. So if you have say 10 hectares of land, so you want to know per hectare what is the stand basal area. So that is the basal area of all the trees in that area. It's a good indicator of crowding in an area. How crowded are the trees in that area? Okay. So the more the stand basal area, the more is the crowding. And SBA, how do you measure the SBA? Either directly by using basal area of individual trees. If you know the basal area of all the individual trees in that area, you can use it directly, or indirectly by using spacing factor. Spacing factor is how far are trees from each other in your stand. So what is the space between the trees in your stand divided by the diameter. So spacing factor for a particular stand of trees is the average distance between trees divided by the average stem diameter. So what is the average distance between any two trees divided by the stem average stem diameter? So that is spacing factor. Okay. So stand basal area is sum of basal area of all trees in an area, and it is expressed as a per unit area of land, and it can be either measured directly by using basal area or by using spacing factor. Fine. So here you can see there are 1, 2, 3, 4, 5, 6 trees in this area, and you have a plot boundary of a zero point 0.1 acre fixed radius sample plot, and you have these. So it's a sample plot, and you have these six different trees. So from these trees, you calculate the basal area for each tree by using pi d square by 4, and then you add all of these. So basal area of 1.1 acre plot is 4.193 square feet. So what will be the basal area per acre? So you multiply it by 10, and it will become 41.93 square feet per acre. Right? I hope this is clear. If you have any doubts, you can ask me. And then, if you look at stand basal area, and if you compare it or if you plot it against the relative spacing, you see that stand basal area is high if the spacing between trees is low, and as the spacing goes up, the stand basal area decreases. Basically, um, if as the spacing between the trees goes down, then the basal area, stand basal area for that particular plot keeps decreasing. So if you look at this here, if these trees were very far apart, you would not have the same amount of basal area in this land, right? If you had only these four trees and these two were not there, so the spacing between all the trees was higher, average spacing, then your stand basal area would be lower. But if the stand basal area is high, the spacing factor is low. Okay. So you can see that they have this negative relationship. Okay, so this was all about what was taught during this week's lectures. If anybody has any doubts, you can ask me. If there are no doubts, let's proceed to the quiz. You can either, it's actually helpful, just type your answers out into the chat box. Don't unmute yourself and tell the answers. But yeah, if you want to, you can unmute yourself and tell the answers. Anything works. Okay. Okay. Moving on to the quiz. First question is, for absolute form factor, the reference for the base of the cylinder is, what is the reference? Where do you take the diameter from for the absolute form factor? Is it the base of the tree, the breast height, 10% of tree height, or 20% of tree height? So where do you take the diameter from if you want to measure the absolute form factor? Anybody? People start sending your guesses in. Somebody saying A, base of the tree. Yeah, others? For absolute form factor, what is the reference that we use? Do we take the diameter from the base of the tree, from the breast height, from 10%, 20%? Okay, nobody else wants to answer. Anyway, so Tarzia, you're correct. It's basically from the base of the tree. So for absolute form factor, the reference diameter is taken from the base of the tree. In similar triangles, if a tree's shadow is 15 meters and an object is 1.5 meter, casts a shadow of 3 meters, what is the tree height? So the tree's shadow is 15 meters, object is 1.5 meters, and it casts the shadow of 3 meters. So what is the tree height? Everybody gets their notebooks and pens or whatever in order to. Some of these questions will be numerical type because we have a lot of calculations in this week. So, but yeah, so we discussed how similar triangles are used to measure a tree's height. So you can Draw it out. You have a tree. The tree's shadow is 15 meters, and you have an object of 1.5 meters, and the object's shadow is 3 meters. So, what is the height of the tree? B, 7.5 meters. Others? D. Other people, are you taking long to take a guess or to calculate? Are you trying to find notebooks, pencils, pens? So, say your tree's height is h. H by 15 should be equal to. Okay. You guys are correct. The answer is 7.5. So, okay, I can't draw here, but if you have a tree, say of height h, and this is 15 meters shadow, and then you have an object 1.5, shadow is 3 meters. So, h by 1.5 should be equal to 15 by 3. Okay, moving on. For a normal form factor, the reference for the base of the cylinder is. So we discussed for the absolute form factor. For the normal form factor, the reference is what? Base of the tree, breast height 10%, 20%. Okay, somebody is saying B, breast height. Others, for the normal form factor, the reference of the base of the cylinder is. There are three types of form factors we discussed. One is absolute, one is false, and one is normal. So, absolute in the previous question we found is the base of the tree. Now there is left is false form factor and normal form factor. And three people so far has said breast height. Anybody else? Okay. So basically, all of you are wrong. The breast height form fact is used for the false form factor, but the one for the normal form factor is actually 10% of the tree height. Okay. We discussed this, but yeah, keep it in mind. For the normal form factor, it's 10% of the tree height. The DBH is actually used for the false form factor. In India, the breast height is considered to be 1.37 meters, 1.47 meters, 1.57 meters, 2.47 meters. So, what is the DBH? Oh, sorry, the BH for India or in general? What is the breast height? Okay, somebody saying B, 1.47. There's one A, 1.37. A, A. Others? Yeah, so the correct answer, as we discussed so far, is basically 1.37 meters. So, in most countries, it's 1.37 or a simplified version of that, 1.3 meters. And it's basically USA and stuff, which is USA also has 1.37 meters, and Korea and Japan has 1.2 meters. So, above that, usually, yeah, it's nothing big above that. Measurement of height based on similar triangles comes under similar measurement, dissimilar measurement, indirect measurement, direct measurement. So, when you're measuring the height of a tree using similar triangle method, what does it come under? Which methodology? A very simple question. So, which kind of methodology uh, includes measuring the tree height based on similar triangles? You're saying similar measurement? Anybody else? Four people are saying similar measurements, probably because they're following just similar triangles and similar measurement. But I said there are two types of measurement ways you can measure height in, dash and dash. And then there's certain things. So which one does how similar triangle come under? C. So yeah, people who said C are correct. There are two ways of measuring height, indirect and direct. Direct ways are using like a direct rod or climbing the tree and measuring it. Indirect was using trigonometry or similar triangles. It's not similar measurement. Okay, moving on. Again, get your notebooks out. For a tree with a DBH of 45.6 centimeters, a height of 27 meters, and total stem volume of 1.78 cubic meters. The artificial form factor for the tree is, the artificial or the false form factor of the tree is what? So we discussed a formula which related volume with DBH, height, and form factor. So can you tell me what is the total stem volume? Okay, people are saying zero point 0.1. The correct answer is zero point 0.4. Okay. So how have you guys calculated? 1.4 is there. Yeah. So basically, we saw that volume is form factor into dBH into height. So form factor would be volume divided by dBH and height. And because here dBH is in centimeters, you'll have to convert it into meters, divide by 100. So 1.78 divided by zero point 0.4 into 27. Is that how you guys calculated?
இன்னைக்கு ஸ்ரேகா எங்க எங்க ஸ்ரே ஆமா ஸ்ரேகா ஸ்டோரி போடுறா பாரு எனக்கு அதுதான் தாங்கல எங்க எங்க ஸ்ரேகா
Mm. This seems to be a little confusing. One second. Oh, let me see how I can get the pen. Okay, volume we saw is equal to, one second. Yeah, volume is equal to form factor multiplied by dBH multiplied by height, right? So form factor, sorry, should be able to, should be V. Sorry, this is not D, right? It's basically, it should be pi d square by 4. This should be basal area, not D. This should be basal area. So that's basically, I think, where everybody is getting it wrong, right? So if you guys calculated by using basal area, can you do it once more? Don't use dBH directly. It's basically form factor into basal area into height, and basal area is pi d square by 4. So that's probably where you guys are getting it wrong. Is this clear to everyone? Like, other people who are saying zero point 0.1, can you redo this and check if you're getting zero point 0.4? Okay, anyway, if nobody's trying it out again, go back and check it. It's basically you don't have to use dBH directly if you guys have been doing that. Volume is form factor into basal area into height. I also got confused for a minute, but yeah, I hope if you do it again, you will get the correct answer. Moving on to the next question. Consider a stand of eucalyptus trees that are on average 30 centimeters in height and spaced on a regular 3 meters grid. Can you find the spacing factor? So we just discussed what's the spacing factor. If you remember the formula, calculate the spacing factor using the average diameter, which is 30 centimeters, and they're spaced out on a regular 3 meter grid. Give me 1 minute. Yeah, I'm back. Sorry. So you guys are saying B? Yeah, very well. The correct answer is B. It's basically 300 divided by 30 because it's a 3 meter grid. So that becomes 300 in centimeters and you divide it by 30, right? The stand basal area is the total basal area of all trees per unit dash. Very simple question. Stand basal area is total basal area of all trees per unit. Volume, height, ground area, age. C, 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 correct. So basically it is per unit ground area. We just did the previous question based on that. So yeah, stand basal area is the total basal area of the trees divided by ground area or per unit area. A tree has a DBH of 25 centimeters. Can you calculate its basal area in meter square? So the DBH of the tree is 25 centimeters. So we want to calculate the stand basal area in meter square. Zero point 0.049. Very good. That is the correct answer. Here is the formula for basal area for people who have not, who don't remember it, but I anyway said it. So it's 0.049. People got it correctly. Others, if anybody has a question in any of these questions, please ask me. If you're not able to calculate any of these, or most of these are straightforward if you apply the uh, formula. Okay. 1 second. I'm running low on battery. I will have to change positions. Give me 1 second. Today everything is going wrong. Sorry, I'm inside with the class because my battery is low.
இந்த ஸ்கூல்ல ஆனா அங்க நல்ல வாய்ப்பெல்லாம் ஏற்படுத்திடுவாங்கடி.
Yeah. Hello. I hope I'm still audible. And yeah, coming to the next question. Diameter over bark and diameter under bark and diameter thick and bark thickness are related as. So, which of these formula tells you the correct relation between DOB, DUB, and TB? Is DOB is equal to DUB plus TB minus TB plus 2 TB minus 2 TB? Which one is the correct formula for DOB, DUB, and TB? Anyone? People, take a guess. It's quite straightforward. We discussed it. We saw that image also, where DOB is the diameter over bark, diameter under bark, and bark thickness. How are these three related? Okay. Oh, I lost my network connection. Ayo. Hello. Sorry about the network connection. Am I audible? And is my screen visible? Yeah, so we were at this question with the diameter over bark and diameter under bark. Sorry, my network connection is a bit patchy. I am in a field station and we don't have much internet connection here, and that's why, yeah. Uh, anyway, I hope I'm audible. And the correct answer to this question is actually, yeah, diameter over bark is under bark in plus 2 TB. Yeah, you're correct, Darshini. It's basically DOB is equal to DUB into 2 TB. Very good. Next question is, oh, the answer is here itself. Sorry. So if the angle between a tree and the line of sight is 45 degrees and the horizontal distance is 20 meters, so you have to basically calculate height using tan theta. So tan theta for 45 is 1 by 2, and that will give you 20 by 2, which will be 10. So, sorry, the answer was already given upfront. But yeah, so if you guys calculate it on your own, I think you will still be able to get it. I explained it. So, if from the line of sight, the angle between a tree and u is 45 degrees and the horizontal distance is 20 meters. So if you use tan theta, it will be half of that, 10 meters. Next question. For false form factor, the reference for the base of the cylinder is. Okay, we discussed this in the previous questions where we looked at for the other ones. So, what is the reference for the base for the false form factor? Base of the tree, breast height, 10% height, or 20% of tree height? Other people, would you also like to take a guess? For the false form factor, for the artificial form factor, what is the reference of the base of the cylinder? There are two people saying breast height, and one of you saying base of the tree. Other people, okay, since there are no more guesses, the correct answer is breast height. As we discussed, for the absolute form factor, it is base of the tree. For false form factor, artificial one, it's breast height. And for the true or the normal form factor, it's basically 10% of the tree height. Okay. Moving on to a tree has the DBH as 30 centimeters. What is the basal area in meter square? So a tree's diameter at basal height is 30 centimeters. So what is the basal area? A 0.071. Others, have you calculated what is the basal area? There are two people saying 0.071. Other people, yeah, very good. The correct answer, according to me, also should be A. One second. So in meter square, it should be zero point 0.3. So if we have dBH 30 centimeters, so it will be zero point 0.3 meters. And we have pi into zero point 0.3 into zero point 0.3 by 4, which is equal to pi into 0.09 by 4, which comes out to be 0.071. Right? Everybody is getting 0.071, or is it just me? Okay, somebody is getting D. Okay. Anyway, I also think the answer to this question should be 0.071. So I'll check it out. But yeah, I think it's A. Next question is choose the correct statement. For a non circular cross section, girth tape overestimates the sectional area. For a non circular cross section, girth tape underestimates the sectional area. For a non circular cross section, girth test tape correctly estimates the sectional area. Or none of these is a correct statement. So, what do you think? Which of these is the correct answer for Somebody is saying A, it overestimates the sectional area. Okay, everybody is saying A. Yeah, the correct answer is for a non-circular cross section, the girth tape will overestimate the sectional area. Mm. So, moving on to the next question. Three trees in a 15 by 15 meter square plot have DBHs of 25, 30, 35 centimeters. What is the stand basal area per hectare? And 1 hectare is 10 by 4 meters. So, okay, everybody is saying 9.6 meters square per hectare. The correct answer is 9.6 meters square per hectare. So, I guess everybody is able to calculate that by now. So, you basically add the DBHs, oh, sorry, the stand basal and multiply it by pi, like calculate the basal area for the trees and then you divide it by the area of the land. So, correct, the answer is A. Thank you. That was all for today. These were all the questions I had. I hope you understood most of the concepts. And if anybody has any doubts on any of the questions, you can uh, ask me now. If people have no doubts, you can leave the meeting. Thank you so much for joining. I hope you had a nice tutorial and you understand things. Sorry for the network issue and all of this. And one of that questions which we think is wrong, I will correct it. I will check that out and I will correct it. Okay. Thank you for joining. Then I will end the meeting if nobody has any doubts. Can we use a calculator during the exam to solve the problem like this? I don't know. I think a basic calculator is available in the computer that they give for the final exam, but you should once still check um with the protocols or whatever, with the rule, with the guidebook that they give about that they some ways they would have written the rules about the exam if they'll provide a basic calculator or not. I think usually in these exams a very basic calculator is provided in which you can multiply, divide, and all of that. Yeah, owing to the time stamp, like because they have a time whatever limit for solving the exam. But yeah, you should still check it out. Don't just take my word for it because yeah. Okay, thank you guys for joining. Bye bye, see you next week.